Thank you, Nora. Thank you as always. Um, homework. Homework grading. Most of the parts are going to be worth 1 or 2 points. And the way that I will grade them is I will grade them 2 points if they're right, one problem if they're sort of right, and 0 points if it's not right. As I've said, there are not many calculations in this class, but when I say half credit, that means if you get the right answer, you jump through hoops, you do integrals, you do three-dimensional integrals, you throw in a contour integral just for fun, and then you do some SolidWorks finite element analysis, you get the perfect answer, and you put meters instead of kilometers, I'll take off half credit, because anything wrong in an answer is wrong. I don't consider sort of wrong, mostly wrong, part wrong, a little bit wrong, they're all wrong. So try to get the answers correct. And remember, most of them will be explanation questions. So as long as you have a pretty good explanation, that should be worth the full credit. And always never be afraid of just saying, well, what's wrong with this? Why did I lose points? Or I think I shouldn't have lost points. All of the homework is submitted online. I think many of the homework problems you can use in a word processor. So you're welcome to just type it in a Word document or whatever text editor you want. Maybe you'll have to paste in a diagram or two, but I would like all homework submitted to be as a single PDF. Please do not send me 7 pictures that you use with Instagram filters so that it has little dog ears. I'm not interested in cutesy homework. I want one PDF, because then what I'll do is I can just load it up on my tablet and grade it there without extra time of converting it and processing it. So please, all of the homework that you submit online on Sakai, make sure it's legible, combine it into a single PDF. It's fine to take pictures with your camera phone as long as you, again, convert it to a PDF. So please look into software to do that. There are plenty of programs that can do that, or just type it on your computer. Most of it can be typed on a computer. A lot of the questions there's room for discussion, and I'm not against people discussing things, but what I don't want you to do is have other people answer your work. So make sure that you can discuss strategies. Let's say that I give you an open-ended problem. That's something where there's a lot of room for individuality. And it can be that you discuss and say, well, that infection preventing suture, maybe one way that I want to do that is to have it degrade by surface degradation. And I have small antibiotics laced throughout there so that over time it releases a small amount of antibiotic that locally prevents infection. And you say, if that person says, okay, great, well, my idea was instead of that, to have it as more of a drug-eluting surface coating, where the surface coating maintains the integrity of the suture as it degrades slowly, and then once the suture is exposed, the suture degrades much more rapidly. So I have more like a hard candy coating on the inside of a soft shell, a soft piece. Both of those work, and I like it when you discuss things, because honestly, I've learned a lot of this material by teaching and discussing it. But please make sure that you're not submitting other people's work with your own name on it. So if there is a gray area, just please don't try me, and I'll find out on exams if you've been cheating on other stuff. Speaking of exams, the exams are open note, open Sakai, open textbook. So basically anything that I provided in this class. Things that it does not include are open your friends, open internet, open cheat website pages. None of those things are allowed. Please keep it to just your notes, Sakai, and if you want the textbook, although again, I don't think the textbook will add very much. I think I said in a previous email about how I was going to give you something like 12 hours to work on the exams. I've changed it a little bit, the formatting. So the way this will work is, again, all of the exams are something that you can write on a word processor. You don't have to download anything, print off anything, write, draw pictures, although you may want to draw pictures. The exam is designed for 75 minutes. I was working on this over the summer when I didn't know if it'd be in person or online. So I designed it to be in the normal 75-minute window. Instead of 75 minutes, I'm giving you 2 hours. So that gives you ample time to download it, look at it, answer the questions, debug problems. When your computer crashes, you can log back on. When your roommate kicks you off because they're streaming videos, then you can get back on after you punch them. All of those things I'm trying to account for with a 2-hour window. But you have a 12-hour window to take that. So anytime between, I think, 8 a.m. and 8 p.m. on exam days, once you log in, a 2-hour clock starts, submit the exam by the end of the 2 hours. All of the material that you type on Sakai will be auto-submitted. If you add any figures, so let's say that you're explaining something and your words don't do justice to your drawing skills, then there will be a link on Sakai where you can submit all of your figures. And let's say that you're writing the exam on question 2C, you really want to make a figure. So on Sakai, where you're answering the question, say, see figure. And then on the assignment link, you can just dump all of the figures that you want, but please do that within 15 minutes of when you complete your exam. I can check the timestamp. Just I don't want to make sure that you say see figure, and then you spend the next 10 hours saying, geez, what figure do I want to see over there? So that'll be how the exams go. It should be ample amount of time. If you have any time problems or if something shuts down on you, I will work with you because I know that this is, to say the least, an unusual time. My goal is to get through the semester without saying because of the pandemic, because if I hear that one more time, I'm going to go nuts. It's been tough for all of us. The final exam, you have a similar structure. It's again designed for 3 hours. I'm going to give you a 4-hour window, 4-hour block of time within a 36-hour window. So pick whatever time it works, and just once you start it, you've got 4 hours. Same deal with figures. If you want to submit them online, you can submit them online after you've completed the exam. Any questions on the homework or the exams?
I have a question, Nari. Can you explain the thing with the figures again? I didn't really understand what you mean before.
Sure, I'll remind you once we get closer to the exam time. But because the exams, you can type in the answer fields, but it's difficult to submit any figures. You're not going to be able to submit figures with the assignment or with the quiz. Once you go to the test/quizzes page on Sakai, you'll take the exam. If you want to add figures, let's say that you draw some figures on a sheet of paper, there's a separate assignment link on Sakai where it would be exam 1, and you would just upload your figures onto the assignment link. So all of your answers should be on the test quizzes interface, but if you have any additional figures, you would just submit them under the assignment page, okay?
Oh, okay, that makes sense.
Okay. Yeah, and again, with those exams, if you have any questions, just ask me. If you had to email it to me, I don't want to penalize people for computer trouble. Anyone else? All right, so that's a big part of the class. The other big part of the class is the final project. Now, the final project will be groups of 3, unless I realize 3 is too many still projects to grade. But you and 2 partners will be working throughout the semester on a novel application of a new or, an existing biomaterial. The project will consist of written and oral portions. What I'm loath to do is to say, this is a project. I trust you're going to work on this steadily throughout the entire semester, and then here's a giant project all due at the last day of classes. I know that you will have a miserable weekend right before because you'll wait till the end. So instead, not only that, I want to also be able to assess multiple things along the way. I want to see how well you presented orally, how well you presented to different audiences, how well you do peer review and support each other. And I want to be able to provide feedback to make sure that you're on track. So the overall goal is to make an NIH grant at the end of the semester. I'll talk about this separately. So once I'm done with the syllabus, I'll talk a little bit more about the project milestones and details so that you can start thinking about that. So more on the project in a little bit. Getting down to over here, this is my usual expectations and policy. So make sure that you come to class. If you can't, for whatever reason, as long as Nora reminds me, all of these classes will be recorded. I will post all of these on an unlisted YouTube playlist. I'll send you the link for that after class today. But give me about an hour after class is done. I'll have that posted as well as my chicken scratch handwritten notes. Between all of those, and if you'd like to refer to the textbook, all of the material should be right there. And it's generally worked out for most people. Unlike in other classes, I will lecture a lot more with PowerPoint and less with writing on my tablet. And I don't want to do death by PowerPoint. What has usually worked well with this class is I usually plan about 50-ish, 55 minutes worth of material to lecture on. And throughout the class, because we're talking about interesting applications, I mean, these are modern tools or historical things that are more important than, I hate to say it, but it's probably more interesting than the hexagonal post-packing structure and how that relates to titanium HCP. Don't nod your head, HCP to BCC. That stuff is cool. Crystallography is awesome. But it might be more interesting to talk about why certain ocular implants can interface with the body versus others, which are more passive. So the class has a lot of discussion, and I would like you to be in class because then you can ask questions, we can have digressions. When you ask me stuff that I don't know, I write it down, I'll look it up the next time and give you some information that's more relevant to what you want to know. So keep that in mind. I'll try to pause during class. It's hard for me to see hands the way I have all of these computer monitors set up. So if you ever have any questions or want to say something, either stop when I pause and talk, or say something in the chat window. But I would like to get some more discussions and a little less of me just ticking through PowerPoint slides. With the PowerPoint slides, I will post outlines of all of those PowerPoint slides with notes, note fields on them, starting around the second week of class. So to give you an idea of what I have, what I'll usually do is I'll post something like this. So I have all of these made up. I'll have my slides. They won't be complete fields. So I say controlled is good, uncontrolled is bad. I have a lot of things I'll fill in over there. There's room for you to enter notes. Typically, students have found it's useful to print these off, or at least have a digital copy, and take notes directly on these, rather than just keeping it in a loose leaf notebook, since it goes better with the PowerPoint slides. Afterwards, I'll post my completed PowerPoint slides as well. But go ahead and download these before the lecture. They'll help you to get the best note taking out of this course. Let me reconfigure. Okay. Anything else on that? So there is a tendency, unfortunately, that people have had to do some degree of plagiarism when they're answering open-ended questions or some research questions. So let me show you an example. This is where I said describe a diagnostic technique, and the one that a few students picked was pulse laser deposition, PLD. And here's the original. It happens to be the first Google link when you type pulse laser deposition. There's my source. And then the student 3 that I got looked like this. Now, why is this bad? It's not necessarily word for word, but you're copying and the idea, and the students here clearly don't really know what they're doing. They're just saying, all right, I take some words and I flip some things around. So flipping things around is still plagiarism. The original says, uses to melt, evaporate, and ionize material from the surface. Melt, evaporate, and ionize. Melt, evaporate, and ionize. Ooh, ionize, melt, and evaporate. Tricky. No, this is all still plagiarism. There's no original thought. It's just the same thing and changed in the order. Highly luminous plasma. That's poetry right there. Luminous beings are we, not this crude matter, as Master Yoda said. But when I see highly luminous plasma, and then I see luminous plasma, and I see further luminous plasma, and I see another highly luminous plasma plume, it's clear, again, you don't know what, not you, the students, have no original understanding of what's going on. If you're doing something like this, how do you approach a problem? Because they may not have been consciously plagiarizing. I have done this before when I was a student, not when I've submitted materials, but you read something, you have it open here, and now you go ahead and you're saying, all right, I'm going to write my own version of this. If you're looking at something and then trying to type your own version, it's sometimes difficult to decouple your brain from doing what they said, because you say, well, it's right there. Let me follow that good example. The best thing to do if you want to write your own material is go ahead and read the source, and then close the source. Write it in your own words. You don't want to be reading over there and saying, all right, the technique of plasma PLD has been for more than a decade. And then you go to your computer and say, for more than a decade, PLD has been used. What's the next sentence? Okay, I'm going to rewrite it in my own words. You want to be able to read a thought and then transcribe the thought over there. So Victoria, with the luminous plasma usually means bright and high energy. So if you were to use it, that'd be okay, but you would just want to be careful about saying something like, produces a transient high energy plasma plume, because that's more or less the same thing. What might be better to say is that the process uses a very brilliant high energy plasma plume, which after blasting the surface causes the material to radiate outwards and deposit on the surface. So I've taken that, I've rewritten it or re-spoken it in my own words, a similar meaning, and I explained what the word luminous means. But it's not so much the use of the word luminous, is that when I see luminous keep showing up in 3 or 4 things that I read, it's the thing that catches my eye. So even though I'm not using software, sometimes it's easy to catch these things. So anyway, the moral of the story is watch out for what you're doing. If you ever try to transcribe somebody else's work, make sure you're not looking at it as you write on it. Okay? Last thing, here's the semester chart, and I'll walk you through a little bit of what the semester will look like. I've got a little bit of introductory material to do and expanding on what you've already done in 209. Those of you that took 209 last semester, excuse me, great. Some of this stuff will be boring. it may have been boring the first time. I'll try to spice it up because I'll connect it to some other things. But there will be some things that are reminiscent of what you've already done, because I know some students have forgotten things since the last time they took my class. My goal in the first third of the course is to really touch on materials and then some specific materials used in the biomaterials industry, as well as some applications. So up until about exam 1, the emphasis is going to be, here's some materials. This is what people use, as well as some focused application. I always talked about titanium alloys. We'll talk about some more specific titanium alloys that are used in medical implants. I'll talk about some ceramics. I always said, if you remember in 209 and 150, metals are really cool. We spend a lot of time. Ceramics, you know, body's okay with them. They're compressive, strong, not great in tension. And then polymers. Ceramics always got this kind of, they got skipped over. But ceramics do all sorts of cool stuff. The body looks at a ceramic, and a ceramic is like a metal that the body can interface with. So we'll talk about specific ceramic materials, how they can cause bioactivity. Like I said, you can get eyes to, the tissue behind an eye to regrow using tricks with ceramics and little glass materials to spur regrowth. I'll talk about some applications like tissue scaffolding and drug delivery, and then additional clinical applications. The goal of this is to prepare you for some of your 400 and up level electives. If you really like the idea of scaffolding, go ahead and take some tissue engineering classes. If you like the drug delivery stuff, that pharmacoengineering track might have some interesting materials applications. So I'm not going to go into depth. I'm not going to make you a drug deliverer. That's a hard word. A drug deliverer, but at least I'll give you some familiarity with it, and then you'll find out if it's something that you like and want to pursue. I'd like to prepare you for those. After the exam 1, we're going to get into a little bit more specific biological interactions. So I'll talk about how do you modify a surface, because it's the surface that interfaces with the body, not the bulk. If you have a bulk, theoretically the bulk could be lead and mercury, but if it's got an inert outside coating, that lead and mercury should stay safe, although don't go putting that stuff in your body. We'll modify the surface and then talk about protein cell interactions, immune response, how the body reacts, and whether things can cause thrombosis, where you get clotting, or obstructions, how it affects the heart, how it affects tumor growth, infection. So this middle part of the course will be taking all of the early stuff and showing how the body reacts. The last third of the course, I have some guest speakers. I have to verify that they're coming, but typically I've gotten somebody that does some work in pharmacoengineering, so materials and drug delivery techniques, and how to use materials to reload and release drugs. Another one that talks about veterinary orthopedics. So he's a surgeon over at NC State at the vet school, and he does dog hip replacements and some of the problems that they have with there. So those are surgical perspectives. And then the middle one is usually tissue engineering, regenerative medicine. So how you take natural polymers and use those to speed up growth. And that'll be some cool stuff, like if you can powder up the lining of a pig bladder, you can make a powder that can regrow tips of fingers. And that's kind of a cool application of just a material to give the body a structure to fill in what's missing. So those will be some guest speakers. And then the last 3 days are your final presentations, which are part of the project. Oh, yeah, final exam. Yeah, that's nice. So any questions on that? You'll notice exam 1 and exam 2, we won't have lecture that day. What I'll do is I'll post the exam that morning, and then I will log on. I'll have my class and my office hours, and if you have any questions, you're welcome to log on and ask me those questions. But otherwise, there's no formal lecture those days. You got enough to do already. So that's a summary of the semester. Are there any questions before I talk about the project?
Just a quick question.
Mm-hmm.
What is the TM and AOAM demarcation?
So these are the textbooks, the 2 textbooks I have. Where are they? Temenov and Nikos and this quartet over here. So those refer to the textbooks and the chapters that are associated with those sections.
Ah, okay, thank you.
Yep. Any other questions? So before I switch off of this syllabus, in the project and the homework, you can see you got homework, nothing coming up for a little while, but I'll try to make sure that you have, that I complete the material that you need for the homework, at least, the week before, so you have a week's worth. But because the homework will require, it'll have material from each of these lectures, that's why it pays to go starting. Answer that first problem because you know how to do it so that you're not struggling at the end with the whole thing. But if you look at the project field, you'll see that there are several milestones. So there's a topic, a pitch, a proposal, a peer review, presentations, and a final report. So let me pull this up over here and talk about the project. So you can read through all of this, but the idea is come up with a new or existing biomaterial and a new technique to apply it there. The overall goal is for an NIH grant, like I said, and an R03 grant. Since you're not familiar with all the NIH grants, there are big ones like the R01. Everybody wants that. It's like 5 years and millions of dollars. And if you get one of those, that's going to help your 10-year package. But an R03 is a shorter term grant. The idea is that's a 3-year project that you can complete. It uses, generally it uses existing techniques for testing, but it uses a novel application. An R01 grant, kind of that hardest one, is novel techniques, novel materials. R03 is a shorter term, novel material, existing techniques. So in this class, we'll talk about testing techniques. If you take a material, how do you know that that material that you just designed in a dish is going to be able to go into a human? Certainly there are unethical researchers that say, hey, it looks good in the dish, and then they implant it in themselves. And great science has been done with that, but I'm not condoning that because there's a whole process that goes from in vitro testing. In vitro means in glass. Make sure it works in the glass setup. And then put some cells, make sure it works with cells. Put some specialized cells, make sure it works with that. Move into in vivo testing. In vivo testing would start with small animal models and then work up into larger animal models and then ultimately human testing. I will not talk about human testing because that is so rife with complications and restrictions, and I'm just not knowledgeable about that. But we will talk about some of the in vivo tests that you can do. So that's what the idea is, that you're going to come up with an idea, back it up, why you think it will work with existing research, propose the tests that you're going to run, and then the hope is that I will give you $500,000 at the end of the semester to go run that. I don't need to say that I will not do that. But here's some examples. So these are student project. This was a student project. So titanium bone screws. This guy somehow knew exactly what I have in my wrist. I have a bone graft and a bone screw from a scaphoid fracture. And my bone screw took, although apparently they have an 80–90% success rate or a 10 or 20% failure rate. And the problem with those is that there's a non-union in the bone. So the bone, it's broken. They put a screw to bring it back together, but it doesn't always grow back. So osteoclasts are what cause bone to regrow. And if there's poor, osteoclast means that they break apart. And there's poor vasculature, there's no help in regrowth, it's breaking down the bone. That means that the bone can fall apart. So what this guy proposed is he's gonna make a bone screw that's hollow, loaded with growth factors. Growth factors help to regrow tissue, such as VEGF and this OPG to inhibit osteoclast activity. So rather than breaking down the bone, he's got something that's releasing it slowly in a gelatin hydrogel so that it lets the bone regrow. And once the bone is regrown, once it gets past that early stage of risk, now it'll stabilize and it'll be fine. So that was his idea. There have been bone screws, so he took a modified bone screw. VEGF is known to promote angiogenesis, so all of this is known things, but the idea with most of your projects is take something that works in a different part of the body. Take something that has another application, combine them. I know it works here, I've got supportive literature. I know it works there, I've got literature. I'm gonna be the first person to put them together, and this is how I'm gonna test it. So he mentioned Yucatan mini pigs. I don't know what a mini pig is, but certain animals are appropriate for certain tests, and this is how they went through that, and he talked about that. So that's an example of a project. Absolutely doable in 3 years, and it has good research. Here's another example. It's a sponge-based hemorrhage controlling device. Major battlefield injury deaths or battlefield deaths are caused by exsanguination or just bleeding out or infection. So one of the best ways of limiting that is if you can pack a wound to prevent it from healing very quickly, then evacuate somebody from a difficult situation, get them to a hospital where they can be treated. But that 12 to 18-hour window might be serious. Or if you take where there's a disaster and hospitals are overwhelmed, if you can just stop something and put it on pause, then you can treat it later when the immediate injuries, the more serious head injuries and stuff are under control. So here's a paper on this. They added coagulants and analgesic drugs. The sponge mechanically expands and seals the wound, but also the coagulants and the analgesics will prevent any infection, promote clotting. It probably will have to be debrided later on and maybe healed, but the point is to prevent bleeding out. And this is emergency care. So that's another thing. You have to worry about the device, how it expands, and how to pack in these drugs, how to make it potentially shelf stable. You don't want to be carrying a refrigerator around with you just in case. Examples of projects that do not work: somebody wanted to build an external artificial uterus. Now that's very noble and that would be fantastic, but that's not easy. You need to be able to exchange blood, remove waste. You need to be able to provide temperature control and fluid environments. That's way too much. They bit off more than they can chew. Your project should be an incremental step over what's been done before and try to combine things that have already worked. So Haley, there'll be groups of 3. So it'll be you plus 2.
Thank you.
All right, so with that, your goal for the next month or 5 weeks, you're gonna come up with a topic, and you have until September. In the meantime, I'll have talked about a lot of examples. I'll have done some background. I'll touch on some existing biomaterials. What I'd suggest is go ahead and start. You're gonna be finding your own groups. I won't be assigning these. Excuse me, although I can help if you don't have a partner. But over the next few weeks, try to find people with similar interests. You don't have to have it nailed down right now, but maybe you say that you have a particular interest in I don't know, an artificial nose to help people that have poor scent, smelling senses or something. Or maybe you have an interest in filtration and you want to come up with some way of doing dialysis in a package. I mean, dialysis is complicated, but if you wanted to do some dialysis, that'd be a little bit more fluid dynamics as well as filtration. The materials focus would be on the filter itself. Maybe you want to work with a different type of joint replacement. Now, joint replacements have been around for a while, but say with a hip, there's a problem with sometimes the hip coming out of place. And maybe you want to come up with a different design rather than a ball and socket. Maybe you'd want something with a gasket there, an additional sealant so that it stays in place and it can't pull out as easily. A catheter. There was a senior design group that came up with a different design of a urinary catheter. That was the PP group, and they had, I think they won the I4 competition. So there are all sorts of devices and ideas that you come up with. So think of something, find some people that might be interested, and that'll be the first step. So the first milestone is a topic. I'm not gonna grade this. The only thing that I'm gonna do is I'm gonna read it over. I wanna see a few citations. I want to make sure that the project is not too much. I want to make sure it's something you can do. And again, you're not devising an artificial uterus. I'll give you a little bit of feedback and I'll check it off. And as long as you submit it and it's got some thoughts, you'll get credit. What I don't want to see is where you just say, crap, we forgot this, and you throw together something. If I give you some feedback and I say, can you answer these questions? If it's minor feedback, there's no penalty. But if you don't do a good job, I'll take off 2 points and say, you need to really think this better. If it helps, come to my office hours and bounce around some ideas a little bit later. I'm happy to help you come up with some ideas. Okay, so that's the topic. The next step a couple weeks later is the pitch. And this is going to be your standard elevator pitch. I'd like one of you, I would say normally to step in front of the class. Instead, you will step in front of your computer and you're going to give a 1 minute less pitch about your idea. I'll talk more about how to do pitches. I've got some pros and cons about that. Again, I'm just looking to see that you've done it. This is to make sure that your project is still on track and so people can see what you're doing. The class will vote and the top 3 people will get additional points on their final project averages. But if you just get up there and do your work, that's fine. That's the minimum, but try to win. And I'll give you $10,000 so that you can start your company because I'm just throwing out money left and right. Back in October 8th, a little after the pitch, you'll have your proposal. Now the proposal is based off of an FRPD proposal at NC State. That's a faculty research project design grant. Yeah, you don't know any better than I do. So it's a 3 or 4 page grant application. It's an internal NC State thing where they want to give you some money because you have an idea. Yeah, right, we do. The NC State wants to give you a little bit of money, not me giving you money. They want to give you a little money so that you can get your idea off the ground and fund a larger proposal. So this proposal will be a rough outline of your project, and it will be useful for writing your later on design project. It'll be 4 pages, and I have some examples posted from previous semesters. And here are the sections. It'll be graded out of 15 points. And I want you I'll remind you of this, don't put your names in the document because the next thing I'm going to do is turn around and send all of these proposals to your peers. So you will get 2 proposals and you will peer review them. I'll discuss peer review and the importance of peer review and how to give effective peer review later in the semester. But all I want you to do is read over the idea and say, this is good, this is bad, here's some suggestions, here's some things that really work. If you can fix this up, it'll be a really strong presentation, a proposal. Between my feedback and the two peers' feedback, you'll have a lot of good ideas to be able to do additional work. I don't know if Zimbabwe is still having the hyperinflation that they did a little while ago, but Naji bucks aren't going to be worth very long. Last thing is, you've done the peer review, now you have a proposal. You have the project over here. And now you're at the end of the semester. The final presentation, I said 12-minute talk. I will assess this based off of how many groups that we have. This will be like a conference talk where you give a little background of your device, what the problem you're solving is, how you propose to solve it, and the results that you anticipate, and the extensions. So I'll give you more information about that, but everybody will be working on this, so you'll have to work as your team. Everybody should speak. I know I said for pairs, I forgot to update that from last year. The final project will be in the R03 format. I'm not going to talk too much about that because there's a lot of stuff on the feedback. So here's the grading rubric for the presentation. You can read through that at your leisure. And then for the final report, the grant, here's a page where you can find information. I've given you each of the sections and approximate word limits. So abstract, relevance, aims, research strategy, future directions, references, and quality, and the grading fraction of those. All of those things are squirrel, but anyway, I got distracted. All of these things are going to be what you're following. And as I mentioned, I have some examples that I've posted online. If you want to see what a real R03 looks like, I don't expect yours to necessarily be as well written as these because these people actually get money, but have some figures, and you can read through these to get an idea of what to expect. So aims, multiple aims. Now, the idea of the whole semester of building up to this, that shorter proposal, that 4-page proposal, that's going to be the outline of this project. So if you get that, get the feedback, you fill in, bulk it up a little bit, add some more specific examples and some references, detail your testing strategy more, and you got your final project. And that'll be 40% of your grade, the whole thing together. So I know that's a lot of information, but are there any questions on any of that stuff? I'd like you to have your groups picked out in maybe 3 weeks so that I can assign groups in the week or two before the topic is due. But at any point, you want to come and chat with me, I'm happy to give you ideas once you have some ideas of your own. But remember, I'm not an expert on every one of these fields. You might know more than I do. No. Anything?
For the references, Dr. Husseini, would you like us to do them in a certain format like MLA, APA? Do you have any preference?
I don't, as long as you're consistent. I would recommend doing something standard. I mentioned like a Nature Science or a Proceedings of National Academy of Science. Just grab one of the big name journals and follow that. I don't think MLA is really a good idea for scientific papers. But you do, and I have better things to do than go through and say, well, use a comma instead of a period. You forgot to double space over there. That wasn't italicized. Just make it consistent. I'm not too concerned about formatting as long as it's consistent. Okay.
Okay.
If you're, I know there are other programs. I used EndNote when I was a student. There might be a citations program that UNC taught you at some point. Those are great because you download the reference from PubMed or Web of Science, and then it formats it for you automatically with whatever you want. Those are probably the best ways of doing your citations.
Okay, thank you.
Mm-hmm. Anyone else? All right. Well, then let me do a little bit of actual material. Some of this is, like I said, some of these slides you've seen before. This is similar to the presentation, parts of it that I gave right before spring break, which was the last lecture that I gave in person at UNC. But let me start out right from the beginning. So this is D.F. Williams. He's a professor over at Wake Forest. And I always show his picture because I just like to look at his hair and say, man, I could have been like that. It's beautiful, luscious. But he defines a biomaterial in the following way. It's a very broad definition. A material intended to interface with biological systems to evaluate, treat, augment, or replace any tissue, organ, or function in the body. That's broad. It doesn't say exactly what it is. So what is a biomaterial? So for example, is plexiglass a biomaterial? You're surrounded by plexiglass right now. That is defining your lab life right now. Is plexiglass a biomaterial? Could it be a biomaterial?
If you put it in the body.
How? So where might you use it? What's the plexiglass is a brand name. What's the more general term for it? Anyone know?
Polycarbonate?
Not quite.
Acrylic or something?
So it's acrylic. Fiberglass is a composite. PMMA, acrylic glass or polymethyl methacrylate, is acrylic glass. And when it's shielding you from your neighbor's breathing, that's not a biomaterial, but acrylic can be used in hard contact lenses. So in that case, it's intended to augment an organ. It's intended to improve your vision. How about titanium oxide, TiO2? Biomaterial or not?
Yes, biomaterial.
Biomaterial, okay. So it could be, what is it, how is it interfacing or what's it doing? Where's titanium oxide show up?
On the outside of your bone screw when it gets put into your body.
Okay, which bone screw specifically?
A
It's made out of
titanium.
what? Yeah. So if a bone screw is made out of titanium, you remember from materials that metals oxidize, and certain metals will oxidize and form stable coating, like titanium. Forms a titanium oxide, so that's interfacing with a biological system because that titanium oxide is inert. The body doesn't react to it anymore. So how is it interfacing? It's augmenting the bone implant so it doesn't cause chronic inflammation. How about a pig heart valve? Is that a biomaterial? Somebody besides Darren. He's busy getting coffee or something. Yes, so Michelle, it is. It's not quite a device, Victoria. It could be used as a device. So Michelle, any idea what would it be used for? How is it a biomaterial? I guess I forgot typing. So for organ transplants, so pig heart valves can be used to replace human heart valves because pig hearts are very similar to human hearts. It would be a replacement, Olivia, you're right about that. The thing about that is it's a natural polymer. It's a natural biomaterial, and natural materials are also considered biomaterials. In this case, according to this definition, it's intended to replace a tissue. It's intended to replace human heart valves. Why use natural biomaterials? We'll talk about those over artificial. You can also use carbon leaf material to be a synthetic valve, but those have problems. Sometimes the body doesn't acknowledge it as being your own. And if you take that heart valve and you're careful, you decellularize it, remove all of the cells that would cause rejection, then you have something that the body says, oh yeah, I know this. It's got a structure to accommodate the host cells, and the host cells can grow in there and occupy that and now take it over as part of the body. How about polystyrene? Biomaterial or no? You think so, Boris?
I'd say so.
Where is it used?
You could use it in like sutures and stuff.
It's not used like that. I still have Tide Pods left over from your class, by the way. Polystyrene is, in fact, there is no application of polystyrene. Polystyrene is a great insulator. It's completely inert, but it's not currently used, approved by the FDA for any applications. So even though it could be used, it's not really used right now as a biomaterial. So what you'll see is that pretty much anything can be a biomaterial provided it has an application. So the corollary to this discussion is then we worry about something called biocompatibility. The application will determine whether material is a biomaterial, but then we worry about biocompatibility, and even then that's a loaded word. So he uses a very appropriate word, which is the ability of a material to perform with an appropriate host response in a specific application. And the clinching word is appropriate. What does appropriate mean? Does appropriate mean no reaction? Does it mean a modest reaction? Does it mean a major reaction? Well, the biggest, most common word that I will use in this class is also my favorite type of disposable diaper, which is it depends. Everything depends. Is appropriate, is it good to have a reaction? Well, it depends. Is it bad to have a reaction? Well, it depends. Your body does not heal unless there is an immune response. Your body does not have an immune response just to drive you nuts when you scratch yourself. The pain from your body is part of the response. And if you don't have an immune response, you don't heal. So appropriate might be to have a low level immune response. Maybe I want my body to be slightly irritated. An example of that is an intrauterine device, an IUD, which causes a low level inflammation in the uterus, which causes the environment to be inhospitable to sperm, but not so grave that it causes major pain to the host. Other examples would be if you want to put that titanium implant, you coat it with a titanium oxide layer because that doesn't react. Or I might coat it with hydroxyapatite, which is a constituent of bone, which will have a great reaction. The body will come in there and break that stuff down and regrow it and incorporate it into the body. So appropriate host response is important. Biocompatibility does not mean everything is fine and fancy and good. It means appropriate to the application. So any questions on those two things? Because good. With those in mind, I want to break you up into some groups. So I'm going to break you up into some breakout groups. What I want you to do for about the next 5 minutes is I want you to come up with an application. Come up with a biomaterial that solves that problem, and then determine what is the desired resolution. So I'll give you an example. With a knee implant, I want the application would be to heal a damaged knee. The material I would use is, let's say, cobalt chromium molybdenum. And why? Because it osseointegrates, it's very stable, and has excellent mechanical strength. What is the desired resolution? What do I want for the end term? I want no interaction with the body on the knee joint itself, but I want it to become part of the bone where it inserts into the bone. So come up with an application, a possible material, and then how it resolves. In the course of 6 to 12 years, does it break down? Does it become part of the body? Does it become one with you? What's the solution? So let's break you all apart. I'm going to narrate what I'm doing, so I'll stop sharing. Breakout rooms, we've got 56 of you. So here you are, you're going to be in some rooms. And then I'll call you back and we can chat about this. So be gone. Some people like their breakout room better than here. Come on, people. So while the stragglers are getting back, I'd like to hear some of your ideas. So the problem, the material, and then how it's going to resolve. And keep in mind, this is, there are lots of things out there. Chances are maybe I haven't heard about all of them, so I'm curious. So anybody want to share something? Who's first?
I can go ahead.
All right, go ahead.
So our group was discussing, particularly like related to implants, like along any, I guess, bone in the body that would be compatible with it, like some kind of bioactive glass that would work as almost like a bone graft for, like, if you really wanted to osseointegrate. Because I guess for some implants you wouldn't want them to be like necessarily welded directly into the bone or something. But in the case of like reinforcing the bone in some position as well, having a glass that will like facilitate like bone growth in a particular area to reinforce the bone if it's weakening, say for like osteoporosis or just in general, if like you want to reinforce any area. We were talking about that. And also like having that, I think in some cases of like bioactive glass, we're also looking into like it's used as a coating to kind of for like antibacterial and antiviral properties as well, to kind of prevent like infection of like joints and things like that. Because the last thing you'd want is like have an implant, be infected and then go through all those like weeks of pain and antibiotics.
So where's it going to be in 10 years? Where will that bioactive glass be?
It'll be, like its materials will be like integrated into the bone structure, I guess.
Yeah, so it'll fly off. So the intended resolution there would be degradation or resorption, that the material will break down. So I'll talk about bioactive glasses. They're pretty cool. They some of the active elements, they can release calcium, and the calcium will then encourage the calcium and phosphorus. It'll give off those, which then causes bone to regrow. And so when they're bioactive, it means they just spur the tissue regrowth. So bioactive glasses are pretty cool. Who else has got something?
Got one.
All right.
Might be common, but for replacements in like skull injuries, or when you need to cover like a defect in like a full-grown adult, like a possible like titanium or stainless steel plate with a porous edge integrated with osteoblast, so that it becomes integrated into the skull, with ideally not having to replace it over the years because they're full grown.
Okay, and so the resolution, what will it be? It'll, in 10 years, it will have what?
It'll just maintain protection of the skull, and the edges will be integrated with bone.
Okay.
And this steel or titanium covering and protecting the area that was compromised.
Okay, so there's an idea. Who else?
I got one.
Yeah.
So our group is doing kind of simple with like a kid or something who's still growing. If you fracture a bone in like multiple places and you need to hold the bits together while it's healing, you might want to have like a bone plate or something that's screwed in. But it would be made out of like stainless steel or something that so it doesn't integrate. And then after it's healed, you can remove it and then let them keep growing.
So stainless steel is a cheap material. It's used a lot, specifically 316L because of the low carbon and it doesn't corrode. But you would use it. Osseointegration, I've always made it sound like, yeah, you always want that. But if you're dealing with a kid needs to have that removed. And if you want to remove something that became part of the bone, you're going to be taking out the bone as well. So there's another thing, and I'll talk about this, and there's a homework problem where there's research done into magnesium implants, where magnesium is a degradable metal, and your body metabolizes magnesium, and it'll flush, you can guess how, excess magnesium out of the body. So it's actually a degradable metal, and it's been looked into for children for that reason. What else?
Our group was talking about like artificial ligaments for, I have an elbow reconstruction.
Okay.
And so it's a permanent solution. So you'd want it to be inert to the body. You'd want it to like resist fatigue, and you'd want it to like promote like integration into the system.
Mm-hmm.
And when we were researching it, they were
where integration of the system in the system.
So they were talking about using like a PET polyethylene and then coating it with something that makes it less hydrophobic. Mm-hmm. So like collagen can actually like attach to the polyethylene fibers and actually like integrate into the muscle.
Yeah. So mostly at the end points, you'd want to be careful about having too much growth inside along the section over here, because then as stuff starts to grow, it can start to interfere with other parts of its motion. So it's usually going to be at the end points where it grafts onto the bone.
Very cool.
From what I know about those. Okay, so artificial ligaments, yeah. I'm sure there are people here that could use some for ACL, MCL, PCL, LCL, all of those. I can see a head nodding. What else? Anybody have anything way out there?
Ours was, I think, a little bit out there.
Okay.
Does anybody else in my group want to speak? No? Okay. Well, one medical issue a couple of us noticed, because we have parents and grandparents who have hearing aids, is they're very uncomfortable, and there's skin that of course lines the ear canal, and there really isn't a material that allows that to breathe and exchange oxygen so that, you know, the skin can be comfortable and the hearing aid can be comfortable to wear. They do have formed hearing aids out of, I think it was it acrylic and silicone, some things that are a little bit more flexible but not breathable. And we were thinking that maybe something more along the line of like a hydrocolloid, like they use the bandages that actually is able to kind of absorb the moisture, would maybe create a more comfortable seal and interface with the ear canal. This would, of course, be kind of short-lived. It would be something that you would have to replace on a regular basis.
Mm-hmm. So silicone is pretty much, any of you that have little earbuds, so there's some silicone right over there. Silicone is a versatile polymer. You can just modify the composition to make it everything from a liquid to a rubbery material to a solid, and it's used a lot in implants. But people have reactions to it. You can cause contact dermatitis in some cases. So that's some of the problems that you're getting. The hydrogel would be interesting, or the hydrocolloid, I think you said, as long as you, like you said, you replace it, because otherwise that's going to absorb water, and that thing could start to get bacterial growth and other stuff, and that could get pretty gunky. But certainly there's always a big problem, not just with the hearing aids, but anything that's on the skin and that can have any sort of rubbing motion will cause irritation. So that's a big area of research. So, all right, well, see, what you've done in your groups is something that we're gonna do a lot in this class, which is to take a problem and to try to figure out what are the desired properties. So what are the design parameters that your device needs? What are you trying to solve? So let me give you one of them, and you can type some answers into the chat window if you'd like. So let's say that I'm working with something simple. Some of you might have talked about teeth. I'm trying to build a tooth, a replacement tooth. And what do I want? What kinds of design considerations do I have for the tooth? So type them in the window. So color, specific, so non-corrosive. It can't break down. Grinding, be a little bit more specific from a mechanical perspective. So probably want to make them out of ceramic, yes, but think about condition or what you want. So hardness. Hardness is along the lines of not breaking down. Strong in compression. So now we're getting to more specifics. Teeth should be strong, but the answer strong is never good enough. Do you mean strong in tension? I'm not yanking teeth out. I'm grinding my teeth and I'm biting on my teeth. So strength and compression. Which other way should a tooth be strong? So resistant to repetitive biting, so fatigue strength in compression. What other mechanical strength? What kind of shear strength? Okay, so this motion over here is shear. That's from grinding the teeth, the whole, you don't want to do that too much at night, but that's involved with there as well. So somebody said earlier, color, yeah, color and appearance, cosmetic is important. Mohs scale is related to its hardness also. Thermal resistance is a good one. If it were to expand or contract, especially when your mouth is exposed to hot liquids and cold liquids, ice cream and then you chuck some coffee, you don't want that thing to expand and have thermal shock. High elastic modulus, you want the material to be pretty stiff so it doesn't deform and just transfer the load to other teeth. If your tooth, when you were biting down, suddenly moved out of the way, then the load would be distributed on the other teeth instead. So when you're looking at a tooth, you got things like compressive strength, shear strength. It has to be inert, thermal resistance, toughness. You want it to be able to withstand some energy without breaking, or resilience if you prefer. Poor thermal conductivity, also how it's attached to the jaw, as was said. But for the tooth itself, then, somebody mentioned it earlier, what would the best material be? So what would you probably go with? Yeah, so based off of all of those things, especially with the shear and the compressive strength, probably a ceramic. Now, epoxy is a composite. Composites are always the wild card because you can get composites to do just about whatever you want. But the quickest thing is a ceramic. And as a result, you might make a tooth out of some porcelain. That's a very common replacement material. It's got high mechanical strength. It satisfies all of those conditions. How about something else? How about we move a little bit into my father's expertise area, which is the Foley catheter. With a Foley catheter, what do I want my Foley catheter to be able to do? So there's a picture. There is a fluid collection device over here. So this goes into through the urethra into the bladder, and then this inflates. There's a hole over there where the urine can drain out, but the inflated area prevents it from pulling further down. There's a way to inflate the balloon, so it's a double lumen, and then there is a collection device, which is the bag that's usually strapped to the knee. So what kind of design considerations would you have over here if you were designing a Foley catheter? Not what material, what would you be looking for?
Flexibility.
Yeah, just type it in there. I'm trying to find my chat window. There it is. So yes, low elastic modulus, high percent elongation. You want this thing to be stretchy. Now, careful, I'm going to pick on you, Victoria, a little bit. Elasticity, you want to be a little bit more specific in scientific terms. If you want to say elastomer, that's fine. Elastomer would mean it's very easy, it's very flexible, it deforms easily with low force. If you want to say it's an elastic material just means that you apply a force and it returns to its original position. Elastic means, in common speaking, like a rubber band. But a metal is an elastic material because you can deform it a little bit and it returns to its original properties. So smooth, absolutely smooth. Inert, yeah. If it were creep, I guess a polymer might have creep, although then you'd have to look at the temperature to see if it's under stress and it's at a high temperature. But creep would cause it to deform. These are generally not kept in for too long, so this is not a permanent implant. Any other design considerations? So non-bioactive, I don't want it to cause I don't want it to incorporate or integrate into the bladder. So inert over there. Low diffusion coefficient for water. That's a good one. That's sort of lumped in with inert, but I don't want water, or in this case, urine penetrating and getting back into the urethra. So for all of these reasons, and I've sort of hinted at it, what material would you pick with? Start with the main categories. Metal? No. Ceramic? No. You're probably going to be with a polymer. So let's further divide it. With polymers, remember we have brittle polymers, semicrystalline polymers, and elastomers. Which one is most likely the proper choice? All right, good. Chat agreement. Elastomer would be the best because it's the most flexible and easiest to move. Now, you could make an argument about a polycrystal, the plastic material, semicrystalline polymer. Where a semicrystalline polymer, if it were a low percent crystallinity or even amorphous, it could be a little bit more flexible. But the way these things are threaded through the urethra, through the outer parts, it really needs to be able to follow the urethra, and the urethra really can't take much impact before it starts to get scratched up. So this material, sorry?
Do they use a tool to insert these and then pull it out?
Not mostly like that.
Mostly feeding? Okay.
And then, so once it's fed into place, there's a syringe, and you fill this balloon up with water so it's drained. Then into here, you insert the syringe, it inflates this bubble, and the bubble prevents it from being withdrawn. Although, especially since this is a problem with older people that may have problems with being aware of their surroundings and suddenly finding something's attached, sometimes these will get removed by patients, which is why there's always some interest in developing a new urinary catheter. But this is the oldest, one of the standard technologies are Foley's. I actually had a Foley catheter when I was 5 years old. I thought it was a rubber band. I didn't know where it went. Nope, there's no wire. There's no guide wire. All right, so that's another device that helps you pick out what you're going to want to do. There are other things like urinary stents. I'm not going to talk about that too much, but here is the profile for the urinary stent. So a ureteral stent. The ureteral stent starts in the bladder. It usually bypasses a kidney stone or a blockage, and then it gets into the bladder over here, and it allows fluid to flow through here, past a blockage, and then all the way into the tube at the end. and then it gets into the bladder, and then it can drain. Notice this from the website kidneystoners.org, which I unintentionally find more funny than it should be. But with this, look at the material property. So if I want something, it's going to be very similar to that Foley catheter. If you read the product description that comes in the manual, you can see some of the things that they cite as being exciting, which is become soft at body temperature, promoting patient tolerance and indwelling stent. What does that mean? So what kind of material is this probably? And what happens, how does it become softer at body temperatures? Think back to your materials class. So not quite a thermoplastic, although it'll have that property. So Caleb, that's it exactly. Remember the glass transition temperature, and I'll remind you of some of these things. I'm kind of doing an overview of the next few weeks. Glass transition temperature is what happens with amorphous materials like elastomers. Below the certain temperature, the bonds are close enough where the material appears a little bit more structured and rigid. As the temperature rises above the glass transition temperature, the molecules become a little bit more energetic and the material becomes more flexible. So below it's like a rubber, above it's, or below it's more like a stiff rubber, above it's more like a more flexible rubbery material. So at low temperatures, this is more easily threaded because it's more rigid. And then once the body raises the temperature of it, it becomes softer and more comfortable. So that's how they designed it. They adjusted the glass transition temperature there. Over here, let's see. So there's a Hydro Plus coating to facilitate advancement up the ureter. So what does a Hydro Plus coating probably mean? It means they trademarked it probably so that they could patent it and make more money. But Hydro Plus probably means what about the surface? You can even read it down over here, and it says it right there. It says it right there.
Hydrophilic.
So it's hydrophilic. This material is hydrophilic, so it slides more easily past the fluid environment. So by designing it to be hydrophilic on the outside as well as on the inside, the urine will flow more fluidly. And also, as it's sliding up through there, it's more easy and more comfortable. The biggest danger would be to damage the person's the ureter or the urethra as it's getting in there. So you would look at this and say, I want to design a new stent. What properties do I want? Well, I probably want it to be hydrophilic. I want it to be smooth. I need some way to insert it, so by making it softer at higher temperatures, we'll make it more comfortable. And then some other mechanical designs that you can read about over here. So that's our goal in this class, especially early on. Take a problem, figure out what the design considerations are. Assess all of our material choices and narrow it down. Say, all right, based off of this, I probably want a polymer. I probably want an elastomer. I don't know what this is made of. It's made out of Percuflex. I looked it up, and then it's hidden behind a patent application that I couldn't find. It's probably some silicone, maybe polytetrafluoroethylene or Teflon, so it has that hydrophilicity, or that smoothness. It's not Teflon is hydrophobic. But all of these things are design considerations. We picked an elastomer. Now you would go through and say, this is probably a class that would work. From there, you would say, all right, I think this will work. Design an in vitro test to do that. Make sure that it passes the mechanical tests. Make sure that it passes the basic cell test to make sure it's not causing inflammation. Go up the scale, up the scale, up the scale. Keep working on all of those things to get there. Hydrophilic prevents, it makes it smoother, and hydrophilic prevents cell integration and protein attachment. The moment you have hydrophobic surfaces, hydrophobic bonds form between protein and surfaces, and then you get protein gunk that builds up, causes cell attachment, and cause major infection problems. All right, so that's a little bit of an overview of the class. What I'll do for the next 2 lectures is a little bit of review and a little bit of new stuff, and then we'll start to move to new materials. I'll stick around for at least the hour if you have any questions or follow-up, but otherwise it's great to see so many of you all after so long, and I'll see you all on Thursday. And for office hours, I'll stop the recording so you don't have to, you can have some privacy.